In this video, we're going to work another simple harmonic motion problem. It's a type of pendulum, but it's a pendulum created by a uniform bar that's been attached on one end and allowed to swing due to gravity pulling at the center of mass. So it says the uniform bar has a mass of 0.6 kilograms and a length of 0.4 meters. So this is 0.2 meters to the middle of the bar, and then of course to the end of the bar is another 0.2 meters. It's made to pivot on the end, making a pendulum. Now that means that right here there's the force of gravity pulling straight down. And that gravity is creating a torque. A torque who has a moment arm right here. That's R. And there's an angle right here that's changing. That angle is theta. So we start with Newton's laws. The sum of the torques about a point, I'll call this point P, is equal to IP times the angular acceleration. The torque needs to have a plus and minus coordinate system. This angle is going positive like that away, and that's considered a positive alpha. So we need to make that the same way on our arrow here. So in calculating this torque, I have the weight, W, the moment arm, which is R, which is in our case L over 2. And then I need to find out how much of the force is perpendicular. Well, this component of the force is perpendicular. That would be the sine function, sine theta, and it's attempting to rotate this bar this way, but a positive torque is in the other direction, so we need a minus, and this is equal to IP. Now IP for a bar is 1/3 ml squared, and this is alpha. So you get that from table or figure earlier in the book. In Giancali, I believe it's from figure 8.21 in Giancali. If you're using a different book, then it would come from another table or figure. Now, looking at this, we can do some things. We immediately see that we can cancel the m's because this is just mg. We can cancel one of the l's, and so we get minus g over 2 sine theta is equal to 1/3 L times alpha. Now, remind you that the harmonic oscillator needs to have an acceleration is equal to minus something time, which is a positive constant, times the displacement. So it needs to be in terms of theta. I'm going to rearrange this equation a little bit. Alpha is equal to, there's the minus sign. I've got a 3 which I'll bring up, 3g over 2l sine theta. This is not a harmonic oscillator unless I can replace sine theta with theta. For small angles, we have sine theta, approximately theta in radians. Remember, we just do not use degrees. So alpha is approximately minus 3/2 g over L times theta. Now this is a harmonic oscillator, provided this constant right here is made equal to the square of the angular frequency. But alpha equal minus omega squared theta for a simple harmonic oscillator. Therefore, omega squared is 3/2 g over L. Now, if we go back and look, we're asked to find the period, not the angular frequency. Well, we can do that. We know that if we take the square root of this, we get 3/2 g over L. The period is omega over 2 pi. So this is 1 over 2 pi times the square root of 2L over 3G. Now you may remember that a simple pendulum has the square root of L over G. So this one has something that looks like a simple pendulum, but it has the square root of 2/3. I'm going to put that to the side, although we don't need it for this particular problem. This is the square root of 2/3 T simple pendulum. You can make a pendulum out of all sorts of things. You could use a hula hoop. You could use a sphere rocking back and forth. As long as you don't place the axis in the center of mass, there's going to be a torque and it's going to want to spin back and forth. The choice will just change in terms of what goes out here because it depends on the moment of inertia of how the mass is distributed. Now, let's just get our final answer here in terms of a number. T is equal to 1 over 2 pi to 0.4 meters over 3 times 9.8 meters per second squared. Checking all our units. Meters will cancel. And then we punch this into our calculator. We got 0.8 divided by 9.8. That's a little bit less than 0.1. Take the square root of it. Divide it by 2. Divide by second pi. And we get that this pendulum is going to have a pretty fast rotation. It's only going to take it 45.5 milliseconds. Now when something is that quick, what usually happens is, well, this is the answer they want, is that it would be difficult for us to measure unless we had a really good measuring device that can measure small times. So what's more common is to look at the frequency. If we look at the frequency, we find that the frequency is about 22 hertz. All right, that's it for this video.